Okay, you guys, so today we're going to talk about refraction and thin lenses. Okay, and what I mean by thin lenses are going to be convex and concave lenses. And we're going to look at this concept from two different ways. We're going to use scale diagrams to figure out the information, and we're going to use formulas to figure out the information. So the outcomes in here are described quantitatively, so with numbers, simple optical systems consisting of only one component for both lenses and curved mirrors. So today we're doing lenses. Wednesday you'll do a lab with lenses, and then Thursday we'll talk about curved mirrors. So that is a green describe. What you actually need to be able to do in here, and there's a bit of a caveat to this. Draw a scale ray diagram for a single convex or concave lens to determine magnification, image distance, object distance, image height, or object height. We'll talk about what those variables mean in a bit. In terms of drawing a scale ray diagram, you have to do it in class. So you're going to have to do it on assignments or quizzes for me and on your unit exam. But you don't have to draw scale ray diagrams on the exam. That doesn't mean you can't, because some of you will find the diagrams easier to use to answer the questions than the formulas. So you can choose which one you want to use. Sometimes you can't use a diagram, you have to use a formula, but some of you will be more comfortable, ultimately be more comfortable with the diagrams. Depends on if you're sort of spatially, like if you have sort of a spatial intelligence, or that's sort of how you like learning, is like kind of like seeing things visually, or if you like doing math. Use a ray diagram to determine the characteristics of an image. So that's been given a ray diagram. Use sign convention to interpret results in terms of virtual, real, inverted, or erect images. Probably the hardest part about this outcome is the sign conventions. Okay, and memorizing them and remembering what signs do. What I mean by certain things are positive, certain things are negative. Solve for any variable in the magnification equation and solve for any variable in the mirror equation. So these are the two formulas that we use. So those are both green. Okay, so this isn't going to be the easiest for all of you to see, but I'll refer to it a little bit throughout. Okay, and there's a breeze in here, which is making it a little annoying. Refraction of light rays will cause an image to form whenever an object is placed in front of a lens, and this image may have different characteristics in the object. So if you want to kind of come up, like those of you that are sort of at the back, if you want to come up and look, it's hard to see, but I've got this candle here, and on this paper here is an image of the candle. It's just it's in the center of that ring, and it's hard to get it out of there because of the height. But you should be able to see the candle, and the flame is just upside down. And I can move the lens around, and the image is still there, but it's much more blurry. It comes quite into focus when you're at the right distance, and then it goes out of focus again when you go this way. I'd be able to get a better image with a different lens. There we go. Okay, that one's pretty good there too. And I'll when I'm done the lesson, you guys can come over kind of into this. But this is basically the setup you're going to work with your lab. Is figuring out the distances between the screen and the lens, and the lens and the object, and then use that to find what the focal length of the lens is. But I find this actually kind of impressive, because you don't think that when you just have a lens there that you will actually get an image. Like basically the light rays that are hitting that candle are causing an image to form on the screen behind it, and that's not really something you expect to happen, but it does. And when I was in here yesterday setting it up, after school when the sun was shining really brightly through the window, I had an upside down picture of everything in the window on this, and it was huge, and it was just beautifully in focus, and it was wonderful. But because we have class in the morning, that's a little annoying. We can't do it. So if you want to come back after school if it's nice and sunny and see that, that was pretty cool, because you could actually see the colors, like the colors and everything. So the stained glass, the balloons that were stained glass that Kennedy made were upside down in it. It was really neat, and I could see the PAL board in it as well. So that was pretty cool. And so it's not just kind of a candle, it's just anything that has light rays bouncing on. And so that's what we're going to talk about today, is sort of the mathematics behind that, or how to figure out what's going on there for measuring different distances. So just a little bit of terminology to start. When we talk about image characteristics, or characteristics, when you're asked to find kind of characteristics of the image, what those characteristics are there's three different areas we look at. We look at magnification or size. In terms of comparing the image to the object is either the same size, enlarged, or diminished. So the first lens I used, the image was enlarged. The second lens I used, the image was diminished. It was smaller. Okay, so this just means, enlarged just means bigger. Diminished means smaller. Then there's attitude. Erect, which means upright. And inverted, which means upside down. And in both cases, the image was upside down. I can actually, okay, the magazine rack is upside down. And you can see the lights on the ceiling on in it, if you look at it. It's in here. And then there's the type of image. It can either be a virtual image or a real image. A virtual image is always erect. It's always right side up. Okay? A virtual image can be seen or photographed, but it's not actually formed on the surface. So remember, virtual image is what you see when you look at yourself in a plane mirror. Light doesn't pass through the image position. It just appears to come from there. Okay, so the light looks like it's coming from where the image is. It's not actually there. A real image is always inverted, so always upside down. It can be formed on a diffusely reflecting surface like a piece of paper. So these are real images because they're upside down and they're formed on paper, and the light is actually passing through the image there. The light is actually going from wherever it is, it's passing through the lens and hitting the image, and that's what's causing it to form there. So there's no way that we can actually use lenses to see a virtual image. It's really difficult, but a real image is very easy. And that, I think, is cool, that you can actually see parts of the room upside down. And then we can, it's not actually used as a characteristic, but we talk about it occasionally in the position of the image, where it's either behind the lens or in front of the lens. So this here is behind the lens, right? So it's on the other side of the lens from the object, and in front of the lens would be over here. Okay. All lenses have focal points. And a focal point is the points where all the light rays converge at or diverge from. Okay. And there's a focal point, when we're talking about lenses, there's a focal point on either side of the lens. Focal length is just the distance from the optical center of the lens. The optical center would be like a line drawn right through the center of the lens to the focal point. Okay, so this would be focal length here, and this would be focal length here. The focal length is dependent on the refractive index of the lens material and the shape of the lens. So I have a number of different lenses here. They're all convex, but they all have different focal points, and that's why like the images show up when the lens is at different positions. That one I can't get. It's too far away. So this one, the focal length is sort of where the light rays in this particular lens converge. Okay. There are two types of lenses, converging and diverging. A converging lens is a convex lens. And this is easy to remember, converging, convex, because they start with the same four letters. When they're talking about lenses on the diploma, they use converging and diverging. When they talk about mirrors, they're going to use convex and concave. And the one thing that's annoying is they're opposite, right? A converging lens is like a diverging mirror. Okay, so when we get to mirrors, the labels are opposite. Okay, we'll worry about that when we get there. So converging lens, it's converging. It causes the light to refract towards the principal axis, and it can form real or virtual images depending on where you put the object. Okay. So what happens there? When light rays go through this, what you would basically have is you might have a light ray going this way, like that, and it will bend and go through the focal point. So wherever no matter where the light comes from, like as long as they're parallel, the light rays are parallel to this principal axis here. That's what that's called, the principal axis. Then that means that the light rays will always converge through. So that was supposed to go through the focal point. It didn't. But it'll always go through the focal point. Okay. And that was the lens I showed you, that where all the light rays kind of converged at the same point, and where they converged was at that focal point. Okay. And this is because they're refracting. A diverging lens is the opposite. Okay, diverging lens is a concave lens. We tend to do more stuff with convex lenses, but concave lenses still come up. But convex ones are more popular, and there's a lot larger range of things you can do with them. Concave lenses always form virtual images that are upright and smaller. Always. And they cause the light to refract away from the principal axis. So what kind of happens here, and this is a bit more awkward to draw, if I have a parallel light ray coming in here, it diverges away as if it was coming from the focal point on this side here. So it's going to bend away like that. This one, it's like it's going through the focal point, will bend away like that. Okay. So what a diverging mirror does is it spreads the light out. And what a converging lens does is it focuses the light to the focal point. One thing you can do, like, is the light, like the light rays, like we're going to make a distinction between what we call real rays and virtual rays. Real rays are always drawn with solid arrows, and virtual rays would be drawn with a dotted arrow. And where it's coming from, like where it looks like it's coming from through the focal point, that would be sort of your virtual rays. This is one lesson that is just ridiculous to try and do on the smartboard with the lines and stuff, but I'm going to try and get through it again. It just the rulers don't work the way they should on this, but we'll see what happens. So what we're going to do is we're going to learn some rules for how to draw ray diagrams, and then we're going to do some practice drawing a few of them. Then we're going to look at the formulas. So when you're drawing a ray diagram, and this is what you have to do if you're not given the diagram on the lens on the diagram already. When we are going to do a few of these as they're coming up, I've drawn the lenses on there. Here, the lenses were on there. I didn't draw them, sorry. I copied them from a book. But sometimes you'll just get a blank grid, and you have to draw the lens on. So if you have to draw the lens on, draw it so that its optical center lines up with one of the vertical lines on the grid. Then draw the principal axis. The principal axis is the horizontal line that is perpendicular to the optical center of the lens. Somehow missed the word there. Okay. Decide on an appropriate scale for the diagram. So one box equals 1 centimeter, one box equals 10 centimeters, something like that. We'll go through this. Label the focal points using the focal length given. Place an upright vertical arrow on the principal axis to indicate the position, size, and attitude of the object. And that's going to be to scale, because these are to scale. And then you're going to use the rules, and we're going to talk about rules. There's 3 of them that work for convex lenses, 2 that work for concave lenses. Draw a minimum of 2 rays from the tip of the object arrow to the lens. And real rays are drawn as solid lines, virtual rays are drawn as dashed lines, and where the rays meet for a real image or appear to diverge from for a virtual image is the position of the image. And then you're going to draw an arrow that then it represents the image. So in terms of our rules for convex lenses, so I have this one diagram on here and I've got an object. That would be my object that I have drawn on there. So I can label that as O for my object. Sorry, it doesn't quite line up with the line, but I had to add that to this diagram. And that's okay, we'll just pretend it goes all the way to the bottom. Okay. Okay, so the 3 rules here are: an incident ray passing through the focal point will refract parallel to the principal axis. Okay, so what that means is if I take a ray, so I'm going to take an arrow, and I'm going to start at my object, and I'm going to draw it through the focal point, and it's going to hit the lens, okay, and you stop when it hits that optical center. So this is passing through the focal point, and all the rays always start, the incident rays always start from the tip of the object. Okay, so it starts at the tip of the object, goes through the focal point, hits the optical center of the lens, and then what happens is it's going to refract parallel to the principal axis. 4 cards. Okay. Yeah. Okay. So then that goes parallel like that. Okay. Okay. Everybody okay with it? Use a ruler. You guys, use rulers. Because these are going to be to scale. So this one is not so vital to use a ruler, but when we do the scale ones, you want to use a ruler because it's going to be the scale. That's a boo-boo. It's been double arrowing stuff when I lift my finger up. So yeah, so there's nothing there yet. We need to have at least 2 rays drawn before we can actually tell where the image is. So then the second rule, an incident ray parallel to the principal axis will refract through the focal point on the other side. It's kind of the opposite. So if I start at my object and I draw parallel to the principal axis, I stop at the optical center, and then it's going to refract through the focal point. Now, something I can tell from this is I have to make this line longer because these will converge at some point. And you're looking for the place where the arrows meet. So I'm going to make these both longer here, and I need to... So they cross somewhere. Now my principal axis there could probably be a little longer. So this line here needs to be longer for what I've done. I've got to fix that. It's not. Okay, and then so now I already kind of know. That means that where these arrows meet, if I now draw an arrow upside down, that's my image. So it's upside down. It's quite a bit further away from the lens than the object was, and it looks a little bigger. Okay, so in terms of characteristics, this one would be inverted, larger, and because it's inverted, it's real. Now, I can also now use my third rule to verify that I've got the right location. And this is where the smartboard, it's kind of iffy because it's hard to get right on the top of the arrows. It's a lot more accurate when you're using a paper and a ruler. An incident ray that passes through the center of the lens will not refract at all. So if you put a ray through the center, it just goes straight through. It doesn't bend, doesn't refract. So if I start again here and I go through the center of the lens, it should also go through that point. And it actually worked on the smartboard for change. Any questions? Okay. So what? Okay. Yep. Yep. Yeah. The one that goes from the object to through the center of the lens always is just a straight line. Doesn't bend. And then these two are just opposites of each other. Okay. Convex lens is way easier to do. Concave, there's more places to make mistakes. These ones are fairly straightforward. The convex lenses are just because you're drawing the rays as if the light is coming from a point, as opposed to it's actually going through the focal point. So we'll do the same sort of thing for the concave lenses, and then we'll do some examples of ray diagrams where we actually have some numbers to work with. There's some information. Okay, so for concave lenses, okay, so everything's the same, right? There's an optical center there. I have a principal axis that's the blue line that passes through the center. I have my focal point on either side of the lens, and I have an object here. An incident ray parallel to the principal axis refracts as if it's coming from the focal point on the same side of the object. So what that means is that if I draw my arrow here from the top, the tip of the object, and I'm going to draw it to the red line in the center, then my ray that comes out on this side looks as if it's coming from this focal point. So it goes this way like that. This portion of it here should be dotted. So what I'm going to do, that's how you're kind of drawing it, but I'm going to change this now. I'm going to actually, oops, make it two arrows. So I'm going to take this back here, like that, make that dotted. Okay, and then I'm going to add in another arrow that comes from it that just keeps going straight, but there I'm going to have to fix it because it didn't actually come right from it. I have to move that down a little. Okay. So like that. The problem with the concave lenses is sometimes once you've drawn your rays, and if you don't have them crossing, you have to look at if there's some place where you can draw them differently, or you can kind of stretch them out either forwards or backwards. Like I might have to actually take this ray back this way. Okay. Okay, and then so that's the first one. And an incident ray that passes through the center of the lens will not refract significantly. Okay, so that's similar to the first one. So then similar to with convex lenses. So if I now draw one that goes through the center, it doesn't refract significantly, it just goes straight. So where my image is right here. Okay, so that's my image. And because one of the rays that forms the image, well, two things. Because one of the rays that forms the image is dotted, which means it's virtual, right? This is a virtual ray. This is a real ray. So because one of the rays that forms my image, or that indicates where the image is formed, is virtual, that means the image is virtual. But you can also tell the image is virtual because it's erect. So since the image is erect, that means it's virtual, and in this case it's smaller. And remember that for a concave lens, the images are always erect, virtual, and smaller. If you're doing calculations and you get an answer that suggests you have a virtual image that's larger than the object, then that means it was formed with a convex lens. Because only a convex lens will give you a virtual image that is bigger than the object. Okay, so we'll do a few of these, and these are really important to use your rulers for. Okay, so in this, we're going to say that 1 square is equal to 2 centimeters. Okay, 1 square is equal to 2 centimeters. So just with that, we can say a few things here. If 1 square is 2 centimeters, that's my focal point. That's 2, 4, 6, 8, 10. So my focal point would be 10 centimeters. So we're not really asked to do that, but I'm just kind of showing you how we use this scale on here. So I start with my 3 rules. This is a convex lens. So the rules that I can use are that a ray that's parallel to the principal axis refracts through the focal point on the other side. And I have a tendency to draw my rays as long as I can, just because you really don't know where that image is going to end up, right? So you want to kind of give yourself as much leeway in terms of so what I mean is don't just draw it at the focal point and stop. Take your rays to the end of the page. Okay, a ray that goes through the focal point on the same side of the lens as the object refracts parallel to the principal axis. So if I go through the focal point here, then my next one is going to refract parallel. So it comes off straight. Okay. Now, and I know I have actually kind of messed up. You guys should get your image to be exactly at 2f. On the other side. Mine is messed up a little bit because this one isn't quite right and I can't get it to adjust. So, and then you can test it with your third rule, which is through the center of the lens doesn't refract at all. It just goes straight through. Okay. So that would be my image. And this is sort of one of the, this also illustrates one of the sort of rules or like something that always happens is when you have an object on 2 times the focal point, the image will always be on 2 times the focal point on the other side. It will always be inverted, which means it's real, and it will always be the same size. So when your object is on 2f, your image will be on 2f. It will be the same size. It's inverted, which means it's real. Right? Inverted and real always go together. Erect and virtual always go together. So if you can find one, you can find the other. Okay. Any questions? Okay. The next one we're going to do is a concave one. concave lens. This is our object here. So our first rule is if a ray that is parallel to the principal axis refracts as if it's coming from the focal point. So it refracts as if it's coming from this focal point, and that ray will be virtual. And then a ray that passes through the optical center, through the center of the lens, doesn't refract at all. So that means my image is where those two meet. My image, it's smaller, as it should be, because a concave lens will always give you a smaller image. It is erect, which means it's virtual. But if you can kind of work ahead of me as I'm doing them, or you can work with me. So we have another convex lens, but now our object is behind 2F. Okay, so it's further away than 2F. So again, parallel to the principal axis, refracts through the focal point on the other side. Through the focal point. So if it goes through the focal point, it refracts parallel to the principal axis. And then the third rule to just confirm is through the center doesn't refract at all. So there's my image, which is inverted, which means it's real, and it's smaller. And we can actually put a number on this because this is a scale diagram. We said one box was 2 centimeters. So that looks to be, I don't know, like if one box is 2 centimeters, that's a little less than 3 centimeters. So I don't know, maybe 2.8 centimeters. How are you guys doing with this? Are you okay? No major issues? That's good. Okay, now we have, again, a convex lens with the object on the focal point, right on the focal point. So that means we can't do the ray where it goes through the focal point and refracts parallel, right? We can only do the ray where it goes parallel and refracts through the focal point on the other side, and then the one through the center. Okay, and what I don't want you to do is panic when you get the other line drawn on there and think you've done something wrong. Because now we're going to draw the line through the center. Okay. So what are we left with? Parallel lines. What do we know about parallel lines? They never cross. Okay? So this means no image. If you had a situation that was similar, where they didn't meet on this opposite side, but they were diverging away, then what you want to do is take them back this way as virtual rays, and they'll meet back here. Because then what happens, like if you have an object that's inside the focal point, okay, what will happen is it'll look like this, except these will be like kind of go like that, but then you can take them back this way, where they'll meet behind the object, and it'll be a virtual image, but it will be bigger. Okay, and there is one like that in your assignment, like in the practice questions to try and do. Okay. Okay, so on to equations. Okay, so you can, if you're comfortable with ray diagrams, there's only certain kinds of questions you can answer with a ray diagram that you actually have to use algebra for. But most of the questions that you're given can be answered with a ray diagram, as long as you understand how to draw it to scale. And and I'm pretty sure in the back of your diploma exam booklet where you take the data booklet out from, there's also like a grid, right? Like so there's a big page of grids like that, so you can use the ray diagram. But there's probably only going to be one at the most question like this on the exam. You do have to, on my test, there will be a ray diagram that you have to do, but then that's the last time you have to do ray diagram if you don't like them. In terms of the formulas, the position, size, and nature of the image produced by thin lenses can also be described as formulas. And there's two. There's the mirror equation, which is 1 over f equals 1 over do plus 1 over di. Okay, where f is the focal length, do is the object distance, like it's let me put this in different words. It's the distance the object is from the lens. Distance of object from lens. Di is the distance of the image from the lens. This isn't an SI formula. It's not a System International formula, so it doesn't have, your distances don't have to be in meters. The only rule is they all have to have the same unit. So everything has to be in centimeters, everything in millimeters, everything in meters, everything in kilometers. But you don't have to convert other than just to get them consistent with each other. This is also a really annoying formula to rearrange. And I don't know if those of you in Science 30 are at the transformers stuff yet, but there's a transformer, or not transformers, resistors in parallel. Resistance in parallel has a very similar formula. But this is on your formula sheet. What I'll show you on here is if you have to solve for, like, so if you're trying to solve for f, then what you have to do is 1 divided by 1 over do plus 1 over di, like that. That's what you'd put in your calculator. If you have to solve for do, it's 1 over f minus 1 over di, and then the same thing. The di one would look the same, but it'd be 1 over f minus 1 over do. That's how you rearrange that. No, you can't. You can't. Only if you have common denominators, right? If you're gonna, like, you can only do that if you're adding by hand and you have common denominators. You'll see that when we go through some examples. So if you're comfortable adding fractions, like without using a calculator, these are actually easier to do, I think, by hand, if you're comfortable with that. And I grew up learning fractions by hand, whereas new generations now are learning fractions entirely in elementary school and calculators. Right? So kids are now being taught that you don't divide fractions by multiplying by the reciprocal. It's you put it in a calculator and get the answer. Yeah. That's not necessarily in Alberta. I know they changed the curriculum in BC to do that. So, which is, I find just ridiculous. Anyway, the magnification equation is magnification, which is M, is equal to HI over HO, which equals negative DI over DO. Okay? DI is still the distance of the image from the lens, and DO is the distance of the object from the lens. The negative in there is important. That's in the formula on the formula sheet. HI is the image height. HO is the object height. And M is the magnification. Magnification doesn't have a unit. It's just a number that tells you, 2 times or 4 times. It's like magnification on a microscope. Right? And you can actually use these formulas to figure out if you know the focal point. You can, if you know the magnification of the microscope, you can use it to figure out the focal lengths of both the lenses, the objective lens and the whatever the other lens is, optical lens. Here, is that it? Is that what it is? The other one is? Okay. And Bryn, your brother got really good. He just would say, I'd say what formula to use, and he'd go hi-ho dido. That's what he called this formula, was hi-ho dido. So I always thought that was kind of fun. Hi-ho dido. Okay, so this is also on your formula sheet, and you only use the portions of it that are necessary, because it's 2 equal signs. Usually what you're doing is using that. Okay? HI over HO equals DI over negative DI over DO. But it can be, you can use magnification equals negative DI over DO, or magnification equals HI over HO. Whereas this one, you need everything in it. Then the important thing here is these sign conventions. Okay? So when you have to make things positive and negative. Important, very important. Okay? Especially these. Real focal points will be negative. Okay, so if you're dealing with a convex lens, you have a positive focal point. So that means a convex lens. Convex or converging. Virtual focal points need to be negative. So a concave lens or a diverging lens will always have a negative focal point. That becomes really important when if you're using that mirror equation where you have to plug in focal length. You have to be very careful. You have to look at the type of mirror it is, or lens it is, and then determine positive or negative. Erect images, so that means virtual images, will have a positive height because they're upright. Inverted images, which are real, will have a negative height because they're upside down. And then that's related to this, right? Height magnification. So if it's above the principal axis, which means it's virtual, the height then is positive. And if it's below the virtual axis, so it points down, then that means it's real and it's negative. These 3 are really important. The image distance we don't use that much, but it's worth knowing that if the image is on the opposite side of the lens as the object, then that's a positive distance, and DI would be positive. If the image is on the same side of the lens as the object, then your image distance is negative. But like I said, it's usually these are the ones, and like this is being the same thing. These are the ones that we're usually using, and it's usually the focal point one that we really have to pay attention to. Okay, so now just a few examples to use the formula. Okay, a 9mm tall object is 32 centimeters from a convex lens of focal length 8 centimeters. Calculate the image location and the height of the image. So 9mm tall object, that's my object height. Okay, so I'm going to put it in centimeters because my other two measurements are in centimeters. So to go from millimeters to centimeters, just divide by 10. The object distance is 32.0 centimeters. And the focal length is 8.0 centimeters. It is a convex lens, so my focal length is positive. What I'm trying to find are my image locations. That means my image distance, how far it is from the lens, and my image height. So how big it is. So I'm going to start to find DI. I'm going to use my Muir equation, right? 1 over F equals 1 over DO plus 1 over DI. So I'm solving for DI. So DI has to be 1 over F minus 1 over DO, which is 1 over 8 centimeters minus 1 over 32 centimeters. And this is one time where I am actually okay if you don't put in units in your formulas. Because this one especially, it's just a lot of stuff to write. Okay, so if you kind of slack off and don't put your units in there, I'm not going to take marks off for that one. And if you're going to put that in your calculator all at once, the only place you need brackets is like that. So it's 1 divided by bracket, 1 divided by 8 minus 1 divided by 32 bracket. And you should get 10.7 centimeters, which with SIGDIGs will round to 11 centimeters. Now, if you're comfortable with fractions, what you have here is 1 over 8 equals 1 over 32 plus 1 over DI. Okay. So 1 over 8 minus 1 over 32 equals 1 over DI. So that one I have to multiply top and bottom by 4. So I have 4 over 32 minus 1 over 32 equals 1 over DI. So I've run out of room, but that gives me 3 over 32 equals 1 over DI, and then you can cross multiply. So 3 DI equals 32, DI equals 32 over 3, which would give you the same answer. But you can't just eliminate the ones, right? You can't just flip everything the other way. Decimal's fine. Decimal's fine. And then we want to find the image height. So we're going to use our magnification equation, and we're just going to use HI over HO equals negative DI over DO. So HI is equal to negative DI times HO divided by DO, which is negative 10.7 centimeters times 0.90 centimeters divided by 32.0 centimeters. So you should get a negative number. You should get a negative number because this is going to be a real image, which means it's inverted. It's upside down. That's why the number should be negative. So you want to be really careful about using your negatives appropriately here because that is something I'm looking for. I don't care about the units, but I'm really looking at positives and negatives if you're using the right signs. So I get 0.3, negative 0.30. If you used a rounded amount, you get a slightly different answer, like you might, but it should probably still be 0.30 with some numbers after that. Oh, there's no unit. It's magnification, so it's just like so you could put an X like for 0.30 times, but centimeters, yeah. Oh, that is height. Yeah, sorry. I think it's like Friday. You don't want a candy? Leo, you want a candy? My husband and I usually call Thursday Mini Friday. So we wake up in the morning, oh, it's Mini Friday, since it's almost Friday. But he calls today Friday because it's the last day, and then all 5 days of the weekend will be Saturday. things you have to pretend to yourself to get through the worksheet, okay? Okay, an object 3 centimeters tall is placed 4 centimeters from a lens. So we don't know what kind of lens it is. A virtual image 2 centimeters tall is formed. So if we look at this, we've got our lens in the middle. The object is 3 centimeters tall. It's placed 4 centimeters from the lens. So maybe this is 4 centimeters in here. So this would be where our object is. A virtual image 2 centimeters tall is formed. Okay, so now the first question, that's a little bit, well, we're gonna actually kind of calculate. But yeah, we'll calculate. Okay. So where's the image located? So we're looking for DI. So we have HO is 3 centimeters, DO is 4 centimeters, and this is HI. Okay, and it is a virtual image, so it will be positive because it's upright, so that height will be positive. So we have HI over HO equals negative DI over DO. So 2.0 centimeters over 3.0 centimeters equals negative DI over 4.0 centimeters. So 8.0 centimeters squared equals 3.0 centimeters, negative 3.0 centimeters times DI. So DI is equal to negative, it's about 2.7 centimeters. And that negative, the image distance being negative, means it's on the same side of the lens as the object. So that would mean it's in here somewhere, right? Like that. That would be the image that's the object, or something like that. Which is similar to a ray diagram we could draw. Let me know if I'm going too fast. Determine the focal length of the lens. So we want to use the mirror equation. 1 over F equals 1 over DO plus 1 over DI. So focal length is equal to 1 over DO was 4 centimeters minus 1 over negative 2.7. And it's important that you include that negative in there. So that should be plus, right? But you should get a negative focal point. So you get negative 0.8 centimeters. The negative focal point means it's a concave lens. So that's part C. And there's actually 2 ways that you can answer part C. It's concave. 1, because there's a negative focal length. So negative F. The other way you can tell it's concave is it's a virtual image that's smaller. And only a concave lens will give you a virtual image that's smaller. Convex lens, if it gives you a virtual image, it will be bigger. Abby, look at her video she's got to watch. It's like an hour long now. Oh well. Okay. 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 So this would be more a standard of excellence kind of question. So this would be like a blue level HMA question, where you have to sort of use. Oh no, it's not. Sorry, I lied. It's a different one than I thought it was. No, it's just a normal question. A concave lens has a focal length of 7.5 centimeters. That means it's a concave lens, so it's going to be negative, right? F is negative. An object is placed 25 centimeters away. Where is the image located? So that's DO. So we just want to find DI is what we're looking for. So 1 over F equals 1 over DO plus 1 over DI. DI equals 1 over F minus 1 over DO, which is 1 over negative 7.5 minus 1 over 25. So negative 5.8 centimeters. Again, notice that the image is smaller than the object. It's negative, which means it's virtual and it's upright, right? And only a concave lens will give you a virtual image that's smaller. Okay, and we have a chart down there. We're going to fill in the parts of the chart that we can from the ray diagrams that we already drew. So we've got this here, so let me just fix some of my lines here. Okay, so, and this is only for convex lenses. Okay, so this is just sort of a rule of thumb in terms of where the object is located, what kind of image you're going to get, and sort of what size that image is going to be, approximately. So we did, if we go back to our ray diagrams here that we did, the very first one we did was at 2F. Okay, so at 2 times the focal point. We got an image that was the same size, was real, so it was inverted, and it was at 2F on the other side. So if we go back here, we can fill that in. So at 2F, the location of the image is at 2F. It's a real image. Okay, so R I'll use for real, V for virtual. It's inverted, and it's the same size. What's another one we did? If you flip back to your ray diagram, what's another one we can fill in? At the focal point? Okay, so where was the image at the focal point? So there's no image, okay? Did we do another convex one? So beyond 2F. So beyond 2F, and where was the image for that one? So between F. So this is between F and 2F. Was it real? Was it upside down? Pardon me? No, this is location of the object, and this is location of the image. Okay, so it was inverted. So it was real. Bigger or smaller? Smaller? Okay. So the 3 remaining rows you should be able to fill out after you've done the ray diagrams in the assignment. Okay. So your assignment is page 217 to 222, numbers 1 to 17. Okay, the first couple of questions are with ray diagrams. And again, if you're understanding the formula and you're finding some of the initial questions simplistic, turn to the end and do some of the harder ones. And I think there's a graphic one in there that will be very beneficial for you to do, because it very much relates to the lab we're going to do on Wednesday. Okay? If you haven't done the reading 68 to 74, that'll also help with the lab as well. Pardon me? What? Oh, yes, go ahead and say hi to her. Yeah. Do you think she's actually want like just, yeah. Okay, go ahead.
I don't know. How much you know?
Ah, you changed my color.
And it's Stephanie, and she's in Florida, and she asked me to send her videos of the lessons so she could keep on top of stuff while she was gone.
I don't know.
I just said, I got your
Somebody want to write one?
Oh, but it doesn't have a test on it. So you have to, because I know it's your test. Oh, yeah. I think I need to give you the notes from yesterday. Because you don't have those notes yet. If you want to copy them, copy them from the recording.
Oh, same.
You should be sure.
I think. Over there.
And if you guys want to go over there and check out the fact that you can see the board and the lights upside down on that page or on the right card, that's what we're doing.
Write something. Hi. Hi. Yep.
I don't know, everything's been said. Stop taking my color. Stop it!
And you're right out. And you're right out. Oh. The microphone's so good.
I know.
Usually the microphone picks up most of the noise in class.
So it's physics, you know.
So you guys can now on your unit assignment do question
Sure.
one.
Are we done?
Bye.
What do you want to know?
1 through I think 13 now. I have to look at something have you got seriously right now.
Oh. Stop it!
Yeah, 1 to 13
Stop it!
is what you can do on your unit assignment now. So I'd like you to have most of you finish 1 to 6, so that means 7 to 13. If you can kind of maybe work on that and hand it in when you come back, or like you can also, you probably actually have time to have lab to do some of this stuff. Lab,
Are we good? Is there anything
and I
else?
actually have enough setups. The only lab I actually have enough setups for everybody.
Really hard.
Is there anything else?
We're good.
Okay, say bye.
Okay.
Bye.
Bye, Abby.
Speaker's over there.
Oh, bye.
Bye, Abby. Stop.